Hola, hola, buenas tardes, bienvenidos. Gracias por acompañarnos. Les damos la más cordial bienvenida a este seminario institucional titulado Tectonic Evolution of the Alisitos Arc, Baja California, que será impartido por la doctora Cathy Busby. Ella es profesora emérita e investigadora en el Departamento de Ciencias de la Tierra y Planetarias de la Universidad de California, Davis. Y para que lea su semblanza, le voy a ceder la palabra a la doctora Elena Centeno, miembro de la Junta de Gobierno y investigadora del Instituto de Geología.
Gracias. Bueno, tengo el gusto de presentar a la doctora Cathy Busby, quien ha sido profesora en la Universidad de California, primero en Santa Bárbara y después ahora en UC Davis. Por más de 30 años ha estado en el sistema de la Universidad de California. Ella obtuvo su licenciatura en Ciencias Geológicas por la Universidad de Berkeley y se doctoró por la Universidad de Princeton. Y bueno, sabemos, todos los que estamos aquí presentes conocemos a Cathy, que realiza investigación en vulcanología y sedimentología en márgenes convergentes, pero sobre todo es una geóloga de campo. Ha trabajado durante muchos años en toda la cordillera de Norteamérica y en particular en la península de Baja California, además de haber participado en expediciones oceanográficas en arcos activos como el de Isuboni. Su trabajo en la caracterización de procesos volcánicos submarinos ha sido extraordinario. Entonces tengo el gusto de presentar hoy a la doctora Cathy Busby, quien recientemente en el 2020 obtuvo el Distinguished Geologic Career Award por parte de la División de Mineralogía, Geoquímica, Petrología y Volcanología de la Sociedad Geológica de América. Cathy, es un placer tenerte aquí. Adelante, por favor.
Gracias. Am I speaking now?
Yeah.
I'm not doing this in Spanish, but you wouldn't want me to do it in Spanish. I could try, but what I'm doing today is giving you an update on work that I've been doing in Baja California in Mesozoic rocks in Baja California. I also have a lot of work I'm doing in Cenozoic rocks on the Gulf of California side of Baja. But I'm not going to talk about that at all today. We're going to look at Mesozoic rocks that are Pacific margin rocks. But also I want to, even though only the audience can see this and not the people that are online, I'm wearing a t-shirt that says Loreto, Baja California Sur. And I'm wearing that t-shirt to advertise that the Geological Society of America is having the Cordilleran section meeting there in April. And it's going to be a great meeting. Elisa Fitzdiaz and Manuel Contreras are running a field trip to the Vizcaíno Peninsula that I want to go on. And there'll be a lot of other good field trips, good talks and everything. So I wanted to advertise that. Okay, we're not going to the Alisitos arc, which is what I'm talking about today, even though people asked if we could, because the Alisitos arc, what I'm talking about today, is about an 11-hour drive from Loreto. And so that was just too far to do that. It's only 5 hours from San Diego, so it would be fun to run a field trip sometime, but we would do it from San Diego. So what I want to talk about today is we're going to summarize 3 of my recently published papers and 1 more paper that's now in review. And we're going to basically follow this outline. First, we're going to look at a very well-exposed and well-preserved crustal section through an oceanic arc. And so this is kind of independent of tectonics. It's if you have a beautifully well-exposed, beautifully well-preserved oceanic arc that's just tilted a little bit and exposed on land, what does it look like? What is the geology like? What is the chemistry like? And so on. So, oceanic arcs, in the modern world, you have to drill. So you've just got one drill core and then a lot of area with just geophysical detection in between. this is a place where you can walk on oceanic arc rocks and see what they look like when they're very well preserved. Then we will zoom out to talk a bit about the regional tectonics of the Alisitos arc. And so I'm going to talk about two papers that came out a couple years ago. One paper with Elena Centeno Garcia here, where we solve a problem that allows us to have the Alisitos arc be a native arc. What is a native arc? An arc is an oceanic arc that formed next to a continent, not far away. So there's been this long controversy about the Guerrero and the Alisitos and Vizcaíno. Where did it start? And some people say those arcs formed way out in an ocean basin far away from the Mexican continent. And other people say, no, they were just right near the Mexican continent. So we're going to look at that. And the second paper on that topic is an overview paper I wrote in 2023 that uses detrital zircon to show that all of those oceanic arc rocks are related to Mexico. They did not form far away. And then last, we'll look at a more specialized study that we've just submitted, where we're looking at the effects of assimilation of deep sea fan sediment on the isotopes in oceanic arc rocks. So basically, when you have a submarine fan that goes way out into the ocean, and then you build an arc on top of that, that will be contaminated by the sediments. It's not continental crust, it's sediments coming from continental crust. So that's a difference we'll look at. So we're going to look at two new papers that I talked about before. But then the other thing is we're also going to make use of two papers that just came out in this book. One paper by Elena Centeno Garcia that is on the Zihuatanejo terrain in the Guerrero composite terrain. And then another paper by Manuel Contreras on the Peninsula Ranges, the Southern Peninsula Ranges. And these are both in a GSA special paper that just came out in my honor. So I'm very, very honored to have these 19 papers come out that people contributed. That's me when I was a youngster. And that's me. Elena took that picture on field tripping in Mexico. So first of all, looking at this arc crustal section, this oceanic arc crustal section. So this is an entire book that we published in 2023. It's a GSA special paper 560. And it also has a big fold-out map that you can see in this picture here. I'm holding the map, and Rebecca Morris, my second author, is holding the book. So it's an entire book. It was too much to put in a series of papers. I just made it into one book. And so this is the cover of the book, and shows you what kinds of things we did in the book. It's mainly geological, and so there was still more work to do on the geochemistry. So mainly what we looked at is the geology of this arc segment and a time slice reconstruction, and then discussed processes, but it was mainly geological. But why did we focus so much attention? Well, arguably, it's the best exposed, structurally intact, and unmetamorphosed oceanic arc crustal section on Earth. When you take an oceanic arc and accrete it to a continental margin, it gets deformed, it gets metamorphosed, it gets faulted. And in this case, it just got gently tilted, and it's not metamorphosed at all, and it's not deformed at all in this area. So that's why we focused here. It's a 50-kilometer long section that exposes the upper crust and the middle crust. And we did mainly detailed geologic mapping, but we also got geochemistry, geochronology, and petrography. And I consider this book that's kind of a photographic atlas of an oceanic arc. So what the outcrops look like, what the thin sections look like, that kind of thing. So there's a poster-sized geologic map, and there's the key just showing you what the units look like. And it focuses, when we look at the early Cretaceous, is the purple rocks that make up the Western Peninsula ranges. And those are oceanic arc rocks. And then the Eastern Peninsula ranges, shown in pink, are late Cretaceous, and those are continental arc rocks. So basically, the oceanic arc evolved in time into a continental arc. So let's look at the Alisitos arc. So it's shown in red here, and it's early Cretaceous oceanic arc. And it is dominated by volcanic rocks, which are shown in red, but there's some plutons that are shown in pink. That formed in early Cretaceous time out in the oceanic realm, and then it got shoved under the Mexican continental margin, and which are shown here in Paleozoic to Mesozoic rocks in blue. And then that was intruded by the late Cretaceous arc, which is continental. And that makes a nice batholith. So we've concentrated in the Rosario segment shown here. And there's a couple of reasons. One is as you get further south in the Peninsula ranges, the exposures get better. It's more deserty. But the main reason is that part is, as we discovered in the 90s, it's really not deformed or metamorphosed. And so in 2006, I first published this paper that showed the Rosario segment of the oceanic arc. And it's fun because it also has, not only does it have the volcanic rocks and the plutonic rocks in this west tilted section, but also there's three basic centers. There's a central subaerial edifice, and then it goes off into the marine realm on either side. So on the south side, it's mainly a volcano-bounded basin that's a low area between volcanic centers. And on the north side, it's a fault-bounded basin, which is a basin that was dropped down along normal faults. So this is an extensional arc. It's got normal faults while it's having the magmatism. And it's got these three different basin types. So this is a longitudinal section going from south to north through the arc. So it's tilted westward, and then you have a view, a cross-sectional view as you go north to south. This is shown with no vertical exaggeration. And so again, we have this central subaerial edifice, the northern fault-bounded basin, and the southern volcano-bounded basin, and syndepositional normal faults. And what's really cool about this is also we can tie all three basins together because of these big explosive eruptions that happened in the early Cretaceous. And so you can correlate individual ignimbrites or ashlow tuffs across the length of this arc crustal segment. So that's what's, for example, shown here in bright red is the tuff of Aguajito, which is a welded rhyolite ignimbrite, and you can track it all the way across this area. And actually, we found it 30 kilometers to the north in other places. Ignimbrites, when you have a big caldera that forms and makes a big explosive eruption, it can make a very widespread deposit. And then the other thing that we can correlate across the length is this abrupt transition that took place from what we call phase 1, which is dominantly silicic, to phase 2, which is dominantly mafic. And so we think that the silicic was during arc extension, and then the arc rifted and the mafic material erupted, and that's phase 2. So, and here, the other thing is that from all the zircon work we've been able to do and some argon work, this entire arc crustal section formed in about 1.7 million years of time. So you can make a whole new crustal section in less than 2 million years in this kind of setting, which is really fun. Okay. I need to be able to keep track of the time. Can I use your, actually. Sometimes I get talking. Okay. Sorry about that. I had to go get my phone. Okay, so we did one really geochemically oriented paper in 2019. This was Rebecca Morris's master's thesis. Thank you, I got warm. The building's cold, but I got warm. And so she concentrated on the southern third of this arc segment, but did a really good job of petrogenetic modeling and isotope work and everything from her master's, published it in Journal of Igneous Petrology. And what she found is, yes, it's an oceanic arc. But also, she was able to get really specific and say that it most closely matches the active rift within the Isu-oceanic arc. So that fit with the geology. I was quite happy because I was like, this is extensional, and then it rifts, and the chemistry did not match the arc front very well. It matched this active rift that's right behind the arc front, but still in the arc. So that was cool. So in the book, we have real general geochemistry and zircon dating and so on. But we didn't do a detailed look at the chemistry, except for in Rebecca's area in the southern third. So that was part of the rationale for involving Manuel Contreras Lopez in this work, to look at the geochemistry of the entire arc in more detail and add in neodymium, strontium, and hafnium isotopes. And we'll see more about that later. But back to just the geology of the Alisitos arc, Rebecca made an interactive 3D oceanic arc crustal model that you can go to on a website, and you can zoom around on a Google Earth image with the map overlaid and click on positions, and a window opens up, and it'll be like, you can sort, like, I want to look at the ignimbrites, or I want to look at the lavas, or I only want to look at the plutons. So you can sort those samples and then click on a sample, and the window opens up, and it gives you the geochemical plot of that sample. It gives you some photomicrographs of that sample. It gives you the major element and trace elements and anything else about that location, like outcrop photos and so on. So we just did this because you could just sort of cruise around an oceanic arc and see what it looks like. Okay, so for the book, I really concentrated on the geological evolution. And so what I want to do is just go over a few time slices of how I think this oceanic arc evolved. So we're going to look at first time slice 1. And this is when there's mainly silicic volcanism. And again, remember, there's a central subaerial edifice, a northern fault-bounded basin, and a southern volcano-bounded basin. And during time slice 1, we have 2 silicic calderas forming. Caldera 1 is in the normal, it's in the fault-bounded basin, and it is sited along a normal fault, and it's subaerial. And the cool thing is that Caldera 1 is intruded by, the floor of it is intruded by a sill complex, really big sill complex. And so if you read the literature on resurgent magmatism in calderas, some calderas, after the big eruption, if they resurge, meaning magma moves back in, there's two ways this happens. One is it comes in as a series of sills, and one is that it comes in as a pluton or a resurgent pluton. And so this case, we have one of each. It's really fun that you can read all about in the book. Caldera 1 is the floor was intruded by a resurgent sill complex, and Caldera 2 was intruded by the Labura pluton. So the Labura pluton fed Caldera 2, and then as we're going to see, it continued to grow. And then time size 2 is when we have this switch to mafic magmatism. And so the arc is now rifting apart at this location. And on the central subaerial edifice, we have these mafic lavas. We in the basins on either side, we have mafic tough turbidites, and also a lot of dikes. So the black lines are dikes, but the dikes do not occur on the central subaerial edifice because that pluton remained active. So in time slice 2, when we go to mafic magmatism, we have this San Fernando pluton being in place and feeding dikes, and we have this Los Materis pluton in place and feeding dikes. But the Labura pluton, which is a granite, more granitic, doesn't have any dikes in it because it was still molten. It's kept getting recharged and growing. And so there's no dikes in this part of the Rosario segment. And then this is bringing us to what you see today, which is basically the Labura pluton continued to grow, and it intruded all of the eruptive products and tilted them. And also this caldera filling ignimbrite got engulfed and swept upward. So this resurgence of the Labura pluton tilted the rocks above it, but there's no tilting of the rocks beyond it. So we think that this is the tilting and the sweeping up is due to resurgent magmatism. So this pluton, a pluton can live for 1 million years or 2 million years if you keep putting mafic magmas in at the base and rejuvenating it and keeping it hot. And we think that's what happened here. So just a quick look at the stratigraphic sections and what the rocks look like. So first we'll look at the central subaerial edifice. And so because of this resurgent pluton coming in here, it's divided into a southern segment and a northern segment by the resurgent pluton. And if we look at the southern sector, what we see is first at the base, we see outflow from the Labura caldera. And then above that, we see the mafic lava plateau. So that's this section on the southern sector. The northern sector is the caldera fill. So it is almost all Labura caldera fill. It's about 3 kilometers of mainly welded ignimbrite with some rhyolite lavas interbedded with the rhyolite ignimbrite. So that was a deep, big caldera. And I'm going to come back to that. Here's the caldera, and it's 12 kilometers across, which is big for an ocean island caldera, but feasible, as I'm going to show you. And again, it's like the first caldera, it's along a normal fault zone. So we think extension played a real role in the generation of these calderas. So the central subaerial edifice, the rhyolites are all really welded. And again, people are like, rhyolite welded ignimbrite in an oceanic arc? But we think that the reason that the ignimbrites are all welded is because the entire arc segment was in a graben, and it kept the ignimbrites confined, so they would build up in one spot and weld instead of flowing out far and cooling off. So they're all welded, and then this is what the mafic lava plateau looks like on the central subaerial edifice. And then for the central subaerial edifice, that's the Libera Pluton, the one that lived the longest, and it is the most felsic of the 3 Plutons. And so you can see it's nice and light colored. We can see quartz and some case bar in addition to plagioclase. Then with the southern volcano bounded basin, what you see at the base first is the phase 1 silicic rocks. They're all non-welded ignimbrites and tough turbidites because they were deposited in a marine environment, a shallow submarine environment. And so the ignimbrites are not welded. They cooled enough to not weld. And there's a lot of turbidites that are completely made of ash. And then we have the transition into phase 2 mafic rocks. There's a huge sill complex that took us a while to figure out. It's like 280 meters thick. And then non-marine welded ignimbrite at the top. So we filled in that shallow marine basin. And this is what the marine non-welded ignimbrite looks like. It's very pumiceous, but it's got some stratification and it's not welded. These silicic tough turbidites, which are, turbidites made completely of ash, and they're fine grained, and they have a lot of soft sediment deformation features. And then this is the non-marine. After we filled that shallow marine basin in, this is the non-marine ignimbrite, and it has a dacite lava interbedded with it. And the southern volcano bounded basin was floored by a pluton that's more mafic than the one in the central subaerial edifice. And it was feeding those dike swarms that we see. And then in the northern fault bounded basin, this had a more complicated history. This started out non-marine, and that's the Caldera 1 that I was talking about earlier, the Tuff of Potrero, and with the resurgent sill complex underneath it. Started out as non-marine, and then it was dropped down into deep water by normal faults, and silicic tuff turbidites were deposited on top. And also this amazing deep water debris avalanche deposit that's about 10 cubic kilometers in volume. It's a big one. And it's amazing because it has blocks of welded tuff that were still hot when they got transported in. So they mixed with the matrix to make pepperite because they were still welding when they came sweeping in as this debris avalanche. And then, then we switched to phase 2 mafic volcanism, and these are beautiful hyaloclastite lobe breccia deposits that you commonly see. Hyaloclastite means fragmentation into glass by quenching against water. And these are commonly seen in drill cores in oceanic arc rocks. And also you see them in subglacial volcanic deposits. But this is a gorgeous section of, so here's the transition from the silicic tuff turbidites phase 1 into mafic phase 2, like that. So it was an extensional arc, and then it succeeded in rifting. And then after that, everything's mafic. This is from the phase 1, and this is a deep water rhyolite fire fountain deposit. These blobs that look like spatter, they are spatter, but they're rhyolite. And the reason that can happen is because in deep water, you can keep the volatiles in solution in a rhyolite magma, and that makes it runny. So it behaves like a basalt. This is Guerrero from Guerrero. Elena was there when I took this picture. And then this is from the upper part where we're looking at the mafic hyaloclastites. And you have, these really irregular lobes of mafic magma coming into quench fragmented material. And then the Pluton under the North Fault Bounded Basin is the most mafic of the 3 Plutons. And this is the one that has the anomalously evolved hafnium and zircon. So that prompted us to look at that in more detail, which we'll look at in a few minutes. So first of all, people kept asking me, why do you have so much rhyolite in the Alisitos? It's an oceanic arc. It should be basaltic andesite, you know? It shouldn't have so much rhyolite. And also, so in the 80s, I started working on these rocks in the 80s. Why is there so much rhyolite in the Alisitos? And then also, why do you have silicic calderas in an oceanic arc? And well, the modern analogs had not been discovered yet. But in the 90s, there was a lot more work, oceanographic work, on oceanic arcs because they're underwater. So you can't just walk around on them. And what was discovered is that oceanic arcs that are forming under extension have a lot of silicic magma, as much as half is silicic. And they also have, and then there was like, some people thought you can't get a caldera, a silicic explosive caldera with a ignimbrite in deep water. The water pressure would keep that from happening. And then people started finding modern silicic calderas in deep water in arcs. So they must happen because they're there, right? So those two things were really, controversial when I was working on these rocks in the 80s and 90s, but not so controversial now. So for example, if we look at the Kermadec-Tonga Oceanic Arc, the Gamble Volcanic Center is an 8-kilometer wide caldera nested inside a 15-kilometer caldera. So even bigger than the caldera I just showed you in the Alisitos Arc by a few kilometers. So I'm in the realm of possibility by modern analogs. And also, they estimate, and here's some pumiceous glassy rhyolite from that volcanic center that they dredged. So in these modern extensional oceanic arcs that are dominated by silicic volcanism, it's slab rollback that's causing the extension of the upper plate. And so Izubonin has the same thing. And the Kermadec-Tonga. There's silicic calderas for a distance of 1,000 kilometers in the modern Tonga-Kermadec arc. So now what they've shown is that silicic magma is a major component of oceanic arcs undergoing extension globally and may dominate in extensional oceanic arcs like the Alisitos. So. Okay, now let's just zoom out and take a quick look at regional tectonics. And first I wanted to highlight a paper that Elena and I published in 2022, which is, there's been now we're gonna look at not just the Alisitos Arc, we're gonna look at the Guerrero, Western mainland Mexico, and we're gonna look at these oceanic arc rocks in Vizcaino. And there's 2 models. One is that all the oceanic arc rocks of Western Mexico, Guerrero, Alisitos, Vizcaino, they're all exotic and formed way out in the ocean basin under a west dipping subduction zone and then got accreted. And one of the arguments for that is, well, here's this continental arc that's on the mainland, on Mexico. So you would have a double arc if it was not exotic, if the oceanic arc was not exotic. But what we did is we looked at the geology of this purported continental arc, referred to as the Nazis Arc. And we looked at the geology in detail and found that it doesn't look anything like an arc. Plutons, it doesn't have big, thick sections of volcanic rocks. It's mainly sedimentary with a little bit of volcanic rock. And so we decided it's just a rift province related to the opening of the Gulf of Mexico, and that we can put the oceanic arc right here offshore of Mexico, and then the continental arc continues on up into California, Arizona and California, Sonora and California and Arizona. So this is the native arc model, that we said works because we don't have this double arc. These are not arc rocks. And then Mike Martini, also on geochemical grounds, showed that those rocks are not arc rocks. They're rift rocks. So that was our paper in 2022. Then I got asked to do a review paper there was a Laurentia volume. It's a GSA memoir. And they wanted to put together Laurentia in time slices. And they asked me to do an overview of Guerrero, Vizcaino, Alisitos. And those I, in that paper, put together as one super terrain, because I think they all formed together right offshore of mainland Mexico. And I summarized basically, well, this model I published in like 1998 that had all the oceanic arc rocks of Baja forming above one east-dipping subduction zone through time. And I kind of expanded on that to also include Guerrero in the 2023 paper. And basically just said that they're all tied together. The Guerrero, the Alisitos, the Vizcaino are all tied together by detrital zircon. And so this is not my new data. This is just me summarizing everybody's published data that was existing at that time, and saying that they're all tied together because they have detrital zircon from Mexico. Why? Well, this is, again, working on other people's work. Here's Elena's work on the Potosi fan, which is a Triassic submarine fan that was fed by erosion of Gondwana. And the Gondwana sands were eroded from the Gondwanan continent and then deposited way out on the seafloor as Potosi fan. And then I coined the term Antimonio Barranca fan for a fan that would have provided more Laurentian kind of detrital zircon. And so you can see both, the influence of both Gondwanan and Laurentian detrital zircon. So very simplified evolution in time slices. I gave just in big time slices in this paper. But this is one thing that we can do with more detailed work. Elena just published a paper in 2025, like in the book in my honor, like 2 months ago, that shows how the locus of oceanic arc volcanism moved around in time. Because basically, when we're looking at all of this, when we're looking at the Guerrero, Alisitos, and Vizcaino all together, we're looking at 100 million years of oceanic arc evolution. From the late Triassic to the mid-Cretaceous, you've got oceanic arc rocks, all with detrital zircon from Mexico. And that's 100 million years is a long time. If you look at Western Pacific arcs, oceanic arcs in the Western Pacific, and at 100 million years, you can have a whole lot of different arcs functioning due to slab rollback, and you close this back arc basin and then roll back the slab here and so on. So I think that is what will be done in the future, is more figuring out how an assemblage like that evolves over 100 million years. But in just a real simple, we're showing here, first in the middle Triassic, we have this passive margin. We're putting turbidites way out on the seafloor. And then in Baja, California, it looks like subduction initiated in the late Triassic. And that formed the Vizcaino supersubduction zone ophiolite. And then moving on to the Jurassic, in Northern California, in Baja, California, it's very simple. There's just, after subduction initiation, you have a Jurassic arc. It's more complicated in southern Mexico, and Elena and I have been debating this for years, because we have this Guerrero, the Guerrero composite terrain has this accretionary complex in its basement called the Arteaga that formed between 227 and 170 million years ago. Now, in this paper, I had a completely speculative model that this accretionary complex formed because some kind of obstacle came in the trench and smashed it. But that may not work. Elena and I have been talking about other possibilities, but we'll move on. So Jurassic shows these oceanic arc rocks, and they're all the way. If you move around in the Jurassic, they're in Baja, they're the Aperos Basin, they're in Guerrero. Geez, Jurassic submarine oceanic arc rocks. And then shown in red is the early Cretaceous marine oceanic arc rocks, the Alisitos, Puerto Vallarta and Zihuatanejo, around the Aperos Basin. And then at 100 million years, the Alisitos arc gets shoved under the continental margin. And from that moment on, it's a continental arc that's undergoing contraction as it sweeps east with time. So presumably slab flattening with time. And then that gets into the whole Mexican orogenic belt, which I'm not going to talk about here. So zooming back in on these anomalous hafnium values in zircon in the Alisitos arc, we're like, why are there evolved hafnium in these zircons in the Alisitos arc? And so I sent Manuel 25 samples from my collection, and he began going to work on them. And so partly what he's done is, with this paper that we have submitted now, just characterize the whole arc segment, the volcanic rocks and the plutonic rocks, their whole rock and major and trace element chemistry, and also the mineralogical makeup of the plutonic rocks is in that paper. But this is a sketch I drew that would explain why we only have sediment assimilation in the northern part of the arc segment that we looked at. And Manuel's going to come up and talk for a few minutes about this sediment assimilation. But this sketch I drew, here we are in the Triassic. We have the Panthalassa oceanic crust. We have these submarine fans coming off the Mexican continent and extending out onto the seafloor. And then the subduction begins within the seafloor. And so in some parts, you have the arc built on top of sediment. And in other places, there's no sediment that the arc is built on top of. So it will be very patchy. Now, when you come to Guerrero, the Arteaga is not patchy. There's a lot of that. But in Baja, it's probably more patchy because you're further from the continental margin. So Manuel, you want to give us a few minutes on?
Good afternoon. Thank you, Cathy. I just talked briefly about the isotope work that we have done in these rocks. So in these diagrams, we can see in blue the samples from the North Fault Bonded Basin, in red the ones from the Central Subaerial Edifice, and in green samples from the Southern Volcano Bonded Basin. In this epsilon strontium versus epsilon neodymium diagram, we can see that samples from the Southern Volcano Bonded Basin show positive epsilon hafnium values. That means that they derive from a mantle-derived source, mantle-type source, depleted mantle. And then we have like relatively small variation in the epsilon neodymium values, while the epsilon strontium values vary between approximately 25 epsilon units. But here the rubidium strontium system is more susceptible to mobilization. Also, strontium, it is a fluid mobile element, so it could be derived from a metasomatized mantle source. And we can see here also that samples from the Northern Fault Bonded Basin plot show a wide variation in the epsilon neodymium values, around 6 epsilon units. And this suggests that they have been assimilated an isotopically evolved material. So in this diagram, we also can see mixing curves considering our most parental melt, this sample, and 3 different continentally materials or end members. This line represents a mixing with Precambrian continental cross, like the Caborca type in northwestern Mexico. These other lines show a mixing line between Triassic metasedimentary rocks that are widespread in the Alisitos Vizcaíno Guerrero terrain, and the other line represents a mixing with Paleozoic rocks that are, right now we only have information from the Sonovari complex in northwestern Mexico. So here we can see that samples from the North Fault Bonded Basin can be explained by mixing between Triassic sedimentary rocks up to 25%. And when we see the other diagrams that integrate epsilon neodymium versus epsilon hafnium values, we also see a mixing line between our most parental rock and evolved isotope component. In this case, it considers like a 15% of contamination with Paleozoic sedimentary rocks. We can say from these 2 diagrams that it is kind of clear that there is no involvement of Precambrian continental cross in the genesis of these art magmas, and the isotope evolved composition could be explained either by Triassic sedimentary rocks or Paleozoic sedimentary rocks. And in these other diagrams, we can see a compilation of data from southernmost Western Peninsular range, just rocks. The next slide? Yeah. Thank you. So in the black dots represent Jurassic rocks, gray correspond to early Cretaceous rocks, and in this epsilon strontium versus epsilon neodymium space, we can see also a trend from mantle-derived rocks to evolved composition. In this trend, the most primitive rocks correspond with the Jurassic oceanical rocks, while the relatively evolved composition correspond to the early Cretaceous rocks. And when we compare with the late Cretaceous rocks that correspond to the continental arc, we see more evolved isotope composition in these diagrams. We also present a compilation of hafnium isotope data that is presented in whole rock that correspond with the solid symbols, and also with zircon data that correspond to the open symbols. And here we can see like an evolution from depleted mantle values from some of the Jurassic rocks that goes to moderately juvenile to relatively evolved compositions that will correspond with the Northern Fault Bonded Basin rocks. And then we also see late Cretaceous, the continental arc, either in Eastern Peninsular Range, the orange color, and the Western mainland Mexico in green. So there is a general trend that the art became more evolved as it matured in time. Okay, that will be all. Thank you, Cathy.
So just to finish off, so the last 10 minutes before we came down here to give the talk, I got Elena and Manuel to talk to me about what we think are some outstanding big picture questions for the Guerrero, Alisitos, Vizcaíno super terrain. And we just came up with these 4 things. There's lots more, I'm sure. But one is, if the Arteaga is an accretionary complex, where is the arc that goes with it? And so that's one big picture question. I'm not going to say that I have the answers to these. These are just questions, right? Why did the Guerrero composite terrain get accreted when it did? And what was the process involved? What is the basement for the Guerrero, Alisitos, Vizcaíno super terrain? And in Baja, it kind of seems like it's a subduction initiation, if you like. In Guerrero, in mainland Mexico, it kind of seems like it's this accretionary complex. But what was the accretionary complex on, for example? So the basement rocks, I expected when I first started working in the Peninsula Ranges in 1985, I expected to find ophiolitic basement rocks everywhere, and they're just not there. Okay. And then also, if you did this isotopic mixing modeling, like Manuel has done, what would it show for Viscano? Does that have much sediment contamination? It's the furthest probably, unless things have been shuffled up a lot in a strike slip sense, it's kind of the furthest from the continental margin, so it might have the least. Alisitos might have an intermediate. Guerrero definitely should have a lot. I mean, because you see the Potosi-Fan-Arteaga complex underneath the arcs. So it would be fun to do that mixing modeling with the existing neodymium and strontium isotopes, but also more hafnium isotopes are needed because that adds more information. Okay, so questions? 5 minutes left for questions.
¿Preguntas en el auditorio?
Yes.
Hi, Cathy, thank you for the presentation. I think that the harder question that I have is, when did subduction really started along the Pacific margin, and what is the evidence?
Right, and so that is, I guess, Manuel and Elise are working on that now. There's the Viscano ophiolite. It's late Triassic supposedly, but is it really a supra-subduction zone ophiolite or not? And I don't know. But if it is, then you need to have subduction by late Triassic time.
And if it is not, what would have the Pacific margin look like? I mean, was not a subduction margin? Was it transform margin?
California, and there's Permian subduction in California. That's when it initiated in California as the late Permian. And then in the Arizona, you really don't see any Permian arc rocks, but then maybe in Sonora, then you do see some Permian arc rocks. Those are all continental, but yeah. So when did subduction begin under Baja? And southern Mexico is still open to question. Yeah. But I think the Arteaga complex does look like an accretionary complex. It's full of melange. It's got blue schist. It had to be a subduction complex. But where is the arc for it? Yeah.
Yes, my question is,
Take.
hello. Yeah, my question is that you mentioned as the contaminant part of the northern or southern Alisitos arc, sedimentary rocks of Paleozoic age also.
Yeah,
well, my question is, are these rocks actually cropping out the Paleozoic rocks in the area?
No, I don't like it to be Paleozoic rocks. I like it to be Triassic rocks, because you have like in the Southern Peninsula Ranges, I didn't have time to talk about this, but this new 2025 paper of Manuel's, he has maximum depositional ages on quartzose sedimentary rocks, and they're late Triassic and early Jurassic. So there's because I was like, yeah, where are these in outcrop? Where are these? They're in the Eastern Peninsula Ranges. There's tons of Triassic turbidites in the Eastern Peninsula Ranges, but where are they in the Western Peninsula Ranges oceanic? Where are their outcrops? And that's that 2025 paper. There are late Triassic to early Jurassic quartzose sedimentary rocks in the substrate for the Jurassic and early Cretaceous arc.
So. Another short question. How do you explain that the arc is intact? In the sense, intact in the sense that no deformation, no metamorphism. It's an accretionary convergent margin, and you don't have any evidence of deformation and metamorphism.
So you go further north, and in the Sierra San Pedro Martir, that's a big, wide deformation zone.
Sure.
Yeah. But you come down south where we are, and it's really narrow. The deformation zone is really narrow. It is inboard, east of the arc section. I stopped working where it's getting all folded and metamorphosed, but there are folded metamorphic rocks right at where it was shoved under the continental rocks. So, but it's a much narrower band. And yeah, for some reason, domainal deformation can be domainal. I learned that when I was working on roof pendant rocks for my PhD, is that they'll be slammed and myelitized, and then you go look somewhere else and there's this nice factoid. That maybe this is a mega factoid. I don't know. That's not deformed, but yeah, I don't know why.
Yeah, the photographs are very convincing.
Yeah.
There is no deformation.
There's no deformation.
Okay.
Yeah, we have mapped it. You can get the fold out map in detail. But like I said, immediately east, then the rocks are getting folded and metamorphosed. I stopped there because I don't work on that.
Thank you.
Elise.
Thanks, Cathy, for sharing all this vast knowledge on this region. It's really great. Thank you. With regards to the question of Mike on when the subduction started, I think we still need a lot of work to do there. But recent ages on the deformation in the melanges that are preserved both in Cedros and Vizcaíno are around 164, 167 million years old. And the upper plate in the Vizcaíno subduction complex, it seems to be, according to Luis Javier, a PhD student in the institute that I co-teach with Vanessa Colas, but I must say that Vanessa Colas is his main advisor. It seems to be a suprasubduction arc, what would you see in Vizcaíno, but the ages are still unclear because you have the 220 million years old reported by Kimbrough.
Right, the zircon.
But it was obtained with TIMS, I think.
Yes.
Back then, during the 80s.
Yeah.
So that's supposed to be the initiation of subduction in the Triassic that would put that there. But recent ages that Manuel obtained are actually Jurassic as well. So late Triassic as well. So that would be
Late Triassic?
yeah.
Oh, okay. That's fine.
So that
agrees with Kimbrough.
that would agree with Kimberly.
Yeah.
So
But we want chemistry on them too to see if they're super subduction zone or mid-ocean ridge, right?
Well, the chemistry looks more like organic arc.
More like arc.
Rather than supra-subduction ophiolite. So I think probably we're dealing with the arc. And an ophiolite that correspond with the arc.
But it could be subduction initiation.
Absolutely.
Right.
Yeah.
Yeah. Okay. So that seems to be holding up. That subduction began in the late Triassic.
Late Triassic.
Yeah. At least in Baja. We don't know about Guerrero.
I just going to add a comment. Recently in the paper of Elena, she published a age of 180 million years from
That
a
Gabbro?
Gabbro. Yeah, so that is extending a kind of to older ages in
Right, but
Cortes
then I asked her
magmatism
about
in-
that last night over dinner.
oh
Because in her paper, she says there's this 180 plus or minus 2, but it could have lead loss. And I asked her, is Elena still here? Did she have to go to a meeting? Okay. Well, I'm telling you what she told me, which is that George Garrels did that date, but it is single crystal. It's not, batch zircon. But the Gabbro, she doesn't have confidence in that age. So we need. Oh, and also it could be caught up in a shear zone. It may not actually be a block. The Gabbro, the 180 Gabbro. Yeah, it might not be a block in the Arteaga. It could be something in a younger shear zone. It's very oceanic. Yeah. Okay. It has. Yeah. So it's just maybe it needs to be more, redated. I don't know. Right. Right.
Yeah, the problem with that gabbro is that it has very few zircons. It may have lead loss. I mean, it was 4 zircons. So I
4?
would, yeah, yeah.
Oh,
That's why I said it can be lead loss or something else. And because I also consider it to be something younger, but the problem with that gabbro is a banded gabbro, and the chemistry is mid-ocean rich basalt. It could also be just a block from the arc,
yeah.
you know, because the evidence for the subduction of Arteaga being related to an oceanic arc is that there are blocks with oceanic arc signatures and are
In the
basaltic
Arteaga.
within the complex.
Right.
Yeah.
Right. So somewhere there's the oceanic arc that goes with Arteaga.
Which blocks?
Of the blocks, of the oceanic blocks in the Tierra complex. Because
They haven't been dated.
Only the gabbro.
Only the gabbro.
in the paper of 2000 in Journals of American Science and its quotation.
The blocks or the gabbros cut in it? Oh, I don't remember that age.
Yeah, that would be way young.
Where is it?
That would be way young. I'd like to see that because that would be way too young.
Well, there is something, Mike, we cannot take off the model. Arteaga is cut by 153 granite, and it has the deformation related and the metamorphic contact metamorphisms around it, and it's not deformed. So the subduction complex has to be previous to 150, and that's the
Well, I thought
only
it was
thing that we have.
There's 100 and the subduction initiation granted in your 2025 paper.
Yeah.
That's 170, right? And that cross cuts Arteaga as well. Wasn't it 170?
No, it's that one. The 163.
Oh, 163.
163
Okay.
to
Right.
150.
Jurassic.
Yeah.
Though. Yeah.
Yeah.
Yeah. Clearly Jurassic.
Yeah. So
Yeah.
that one is cutting. So Arteaga has to be
Yeah.
older than that.
Yeah. Yeah.
Yeah.
Yeah. I don't want to keep people here longer than they're supposed to be here. But I thank you for showing up in person. And yeah. Thank you. I thought I was done with Mesozoic rocks when I started working in the Cenozoic, and 25 years ago, I was like, Mesozoic is too difficult. I'm moving to the Cenozoic. And then I got dragged back into the Mesozoic.
Okay, so le vamos a dar su constancia a Cathy antes de que se vaya. Muchas gracias.
Oh,
por
thank
tu
you.
asistencia.
Thank you. I'm going to put it on my office door. Thank you. Okay, let's see. I need to eject your USB.
Congratulations.
Oh, thank you.
Why are you talking about something in nature? I mean, it's unique.
I think so, huh? That's a good idea. That's a